Hi, and welcome back. In the last video, we went through Newton's laws in excruciating detail, trying to figure out what Newton was trying to do and what kind of theory Newton's laws present to us. Now, I urge you to go and do some introductory mechanics problems if you feel like you need practice, because in this lecture, I'm going to go ahead and launch into some new tools that we'll need for the material we'll cover in the future. We'll still spend some time just solving Newton's laws, but now with a bit more granularity and detail, and in some harder contexts than you would in, for instance, a calculus-based introductory course. In this lecture in particular, I'm going to cover two new tools. The first one is the use of polar coordinates to state second-order ODEs like Newton's law, Newton's second law. The second is non-dimensionalization, which we'll get to in a bit. Now, first, I want to talk a little bit about polar coordinates, and really that's as a template for how we deal with any other curvilinear coordinate system. In the previous video, we talked quite a lot about reference frames, with a reference frame being defined as a set of axes that might be moving to our original fixed coordinate system. However, even given a single coordinate or a single reference frame, it may be useful to sometimes work in rectangular coordinates, Cartesian coordinates, and in other times to work in polar or some other curvilinear coordinates. For instance, if our problem has a particular symmetry. So it pays to be able to figure out how to restate a vector ODE like Newton's second law in a curvilinear coordinate system. Now, to do that, we're going to need to build some new intuition. I've drawn here a set of coordinate axes. We're going to do everything in 2D and only think about polar coordinates for the time being. Now, imagine that we have a particle that's on some trajectory. Let me draw it in here. So this is the trajectory of our particle. And let's say that at our time of interest, it's at this point, which I'll subscript x naught, y naught. So this is the point x naught in the x direction, and this is the point y naught in the y direction. Now we know, because we have calculus under our belts, how to draw the velocity vector of this trajectory. Because we don't know how fast the particle is going exactly along the trajectory, we don't know how long this vector ought to be, but we do know it should be tangent to the curve at this point. So let me just draw it in. This is going to be our velocity vector, v, for this point in question. And as in the last video, I'm going to use underbars here. Now, notice what I have done here. I drew the velocity vector as if it were originating at this point x naught, y naught. And that's the perspective that we're going to take. You may have heard in high school that vectors are objects with magnitude and direction, but not location. We're able to freely drag them around on the plane. But that isn't the way that we want to think about things in this context. I really do want to think about the vector v as being a vector that originates at the point where the particle is at that point in time, and that's drawn tangent to its trajectory. Similarly, I could think about the acceleration vector at this point, which, if this were on a well-defined curve, which it kind of is here, would point in the direction that goes toward the center of the circle. So if I imagine a circle inscribed in this curve, then my acceleration vector points in something like this direction. Good. All right. And just as before, I want to think about my acceleration vector as being centered at this point. Now, it turns out that in some coordinate systems, it's useful to think of position as a vector that's located at this point as well. Polar coordinates are one of those systems, so let me draw that in. I would imagine making my line from the origin and just putting the position vector in this direction. Now, it's going to run into my title here, so I'll just have to draw it in like this, and we'll have to imagine that it's somewhat longer. It should be exactly as long as this line. This is not always a useful way to think about the position vector as being a vector located at that point, but it is possible in polar coordinates. Now, because I'm thinking of vectors as having different points in space that they're associated to, it stands to reason that I could pick different bases for different points. So let's draw in a second set of coordinate axes here, x and y. And let's consider two different points. Maybe I'll pick one over here and one over here. Now, in the regular Cartesian coordinates that you're familiar with, we pick the same set of two coordinate axes at every point, something like this and this at this point, and similarly this and this at that point. But now that we're thinking of vectors as living at particular locations, it will matter if we choose these points as having different basis vectors. The trick to polar coordinates is we're going to introduce what we call polar unit vectors. What I'm going to do to draw those unit vectors is draw a line from the origin to each of these points. Any vector that's living here is going to use the following basis vectors. It's going to use one vector of unit length that points in the same direction as this ray from the origin. And then we're going to go always counterclockwise, 90 degrees, and draw a second unit vector. This unit vector is called the r hat vector, and this unit vector we'll call the phi hat vector. Wonderful. Now, technically, if I call this point x1, x2, I have to note that this vector depends on, not x1, x2, x1, y1. I have to note that this vector depends on x1, y1, and so does this one. We can do the same thing here. In this case, my r hat vector goes in this direction, and my phi hat vector goes in this direction. And again, I'll call this point x2, y2, such that this can be r of x2, y2, and this can be phi of x2, y2. Wonderful. Now, what's the whole point of this? Well, if I have a trajectory that passes through this point, I ought to use the basis vectors at this point. So let's go back to our original set of coordinate axes. I'm going to erase this r vector because we won't need it here. And instead, I'm going to draw in our set of two basis vectors. Maybe I'll choose a new color just so that that shows up nicely. So here we go. Here's up, and that is not going to work. Okay, that barely works. I won't choose a new color. Okay, so here is our r vector for this point, r hat, I should say, and here is our phi hat vector for this point. Now, in this example, what does it look like the v vector? How could I write the v vector in terms of these components? Well, it looks like it has a positive phi hat component and a negative r hat component if I were to project. The way that I would do that is I would figure out what this angle is. Let's suppose for a second that this angle is called theta. And now I can say the following. V is going to be equal to what? So it's going to be plus the cosine of phi hat, or of theta times phi hat, and then minus the sine of theta r hat. And that would apply for that point in specific. Now, how can we use this to write down Newton's second law? That's a more involved calculation, so I'm going to actually jump us over to the computer to my second setup, where we can do this in Microsoft OneNote with a little bit more flexibility. Okay, welcome to a secondary recording setup that I have. This will allow us to do more intensive calculations in Microsoft OneNote, where I can write things down much faster than on the Lightboard. All right, so let's switch into a screen where we can actually see what's going on. And again, the goal is to figure out Newton's second law written in polar coordinates. So hang on a second. I think, yep, this should just snap. So let's again draw ourselves some coordinate axes and imagine that this is the x-axis and that's the y-axis. All right, wonderful. So now we're going to look at a given point, and we know that the way that we draw its correct basis vectors, no, I've got it, thank you, that we draw its correct basis vectors is to draw a line that goes from the origin to that point, and then we'll have the r hat vector here, and the phi hat vector here. However, what we can also do is draw in where the x hat vector, again the unit vector in the x direction, and the y hat vector would be. And this is going to give us a map. All right, so before we can actually do that, not only do we have these changes in terms of vectors, we also have changes in terms of the point itself. And this is what students may have seen before. So if I call this point xy, I can just as well describe this point not by its x coordinate and its y coordinate, but also by the distance of this line segment r and this angle here, phi. Now notice that this r is a scalar number and this phi is a scalar number, between 0 and 2 pi in fact. That's different from this r hat vector and phi hat vector, though we'll see that there is a relationship in a moment. All right, and by a little bit of trigonometry, we can figure out that there's a relationship between r, phi, x, and y. In particular, x is equal to r cosine of phi, y is equal to r sine of phi. So that would be to go from r and phi to x and y, and r is equal to the square root of x squared plus y squared, and phi is equal to, well, I'm going to say tan inverse, so the arctangent, except I'm actually going to put not y over x, which I could, but x comma y. And this function, which is sometimes in calculators called the arctan2 function, says find the correct quadrant for the angle. And what I mean here is that if I just write tan inverse of y over x, well, y over x up at here in quadrant 1 is the same as this, the y over x for this point, which is in quadrant 3, exactly 180 degrees around from our original point. And arctan, or I should say tan inverse x comma y, finds the correct quadrant for us. All right. So with those out of the way, these transform us from one coordinate system to the other, but they don't tell us about how to change the basis vectors. Let's go ahead and blow those basis vectors up so that we can actually do that. So again, here, actually, oops, keep my color scheme going. Here's my r hat vector. Here's my phi hat vector. And I know that these are at 90 degrees to each other. Then here is my y hat vector, and here is my x hat vector. Now, just from a little bit of geometry, we see that this angle here is theta, but that means that this angle here is also theta. That's going to allow us to project r onto x and y, r hat, I should say, onto x and y. R hat will equal, well, what's the length of this line segment down here? It's going to be the length of this hypotenuse times the cosine of theta, since this is the angle, sorry, this is the side that's adjacent to theta. So this is going to give us the length of the hypotenuse, which is 1 because r hat is a unit vector. So 1 times cosine theta times x hat, because this is in the x hat direction. And then in the y hat direction, playing the exact same game will tell us that we should say plus, and of course this should not be theta, this should be phi. I apologize. All right, good. Now, suppose we do the same thing to the phi hat vector. Well, after a little bit of maneuvering, we can see that this angle is also phi. That's because to get from r hat to phi hat, we rotate 90 degrees, and to get from x hat to y hat, we rotate 90 degrees. So the angle between x hat and r hat must be the same as the angle between y hat and phi hat. All right, so now we have a pretty good way of figuring out what the how we can write phi hat in terms of x hat and y hat as well. Namely, minus sine phi x hat plus cos phi y hat. And I invite you to go and try that for yourself. Okay. So I can also invert these if I want, but I'm actually going to leave it for the time being, because now I want to actually get us to the hard part. Okay, so suppose that I have Newton's second law somewhere. So for some system, I should say. And that's going to tell me that, well, let's write Newton's second law in vector form. F is equal to m times r double dot, and let me actually make sure to write in that this is a function of time. I'm going to presume here, actually, like let's put in our f's dependence on time as well. Okay. And now let me move m to the other side so that this looks like an equation for r double dot of t. Okay, now I'm going to rewrite this left-hand side in terms of basis vectors, and I'll do it in the Cartesian system. So I'll call the x component of this trajectory just x. So we'll have x double dot of t times x hat, and then y double dot of t times y hat. And this will equal f of t over m. Great. All right, so now I'm going to figure out what x double dot is in terms of r double dot, r dot, phi dot, and phi double dot. So let's do that over here. So if I have x, which is a function of t, because again, now I'm talking about the x coordinate of the trajectory, well, as above, I can just rewrite that using this. So the trajectory could also be expressed as some function r of t times cosine of phi of t. Okay, that also allows me to say what x dot is. So x dot of t will equal, I'll need to use the product rule and the chain rule here. So for the product rule, I'll have r dot of t times cos phi of t plus r of t times, okay, now if I need to use the chain rule, I'll first take the derivative of cosine, which is going to give us a minus, and then minus sine of phi of t. And then from the inside, I'll get phi dot t. Good. And there we go. That's my x dot. And furthermore, I can get x double dot. This is going to require even more sort of chain rule shenanigans, but in the end, it's a little tedious, but not that bad. All right, and then minus, like last time, r dot of t, phi dot of t,
sine of phi of t. Great. Next, need to take the two derivatives of this thing. So I will get, actually, it's going to be three parts this time. So I'll get minus r dot of t sine of phi of t, phi dot of t. Next, use the chain rule. That'll give me minus r of t cos phi of t, then phi dot t squared. And lastly, I'll get minus r of t sine of phi of t, phi double dot of t. Wonderful. Okay, now I need to do the same thing for y. All right, and if I really wanted, I could note that both where here and here, I could combine these to give a factor of 2. Okay, but that isn't actually all I need to do. At this point, I actually should try and combine these to figure out what my x and y vectors are. So I think the easiest thing to do is going to be to multiply, to get the x vector, let's say. Let's multiply this first equation by cos phi and this bottom equation by sine phi, and then we'll subtract them. Okay, so for the first equation, where we want to get x hat, we're going to note that cosine phi times r is equal to cos squared phi x hat plus cos phi sine phi y hat. And then we're going to note that sine phi times phi hat is equal to minus sine squared of phi times x hat plus cos phi sine phi times y hat. Now we're going to subtract these from each other. And that's going to cancel this and this, but these two will combine, and cos squared plus sine squared is 1. So this will tell us that x hat on the right-hand side now is equal to cos phi r hat minus sine phi phi hat. We can do the same thing to get y hat by itself. So what do we need to do? We need to multiply r hat by sine phi. And then we need to multiply phi hat by cos phi. And then we simply add these two. Oh, and that should have been phi hat. And once again, we see that we get exactly the cancellation that we need, and find sine phi r hat plus cos phi hat is equal to y hat. Okay, let's go ahead and write those out down here nicely so that we can see what's going on. All right. Now I'm going to use this along with this, and I'm going to plug all of those into this left-hand side. So, oops. And what is that going to give me? Well, there will be a lot of copying, but it's all right. R double dot of t cos phi of t minus 2 r dot of t sine of phi of t. Oops, and I forgot my phi dot. Okay, now I close that. Now I need to multiply by x hat. And x hat is right here, except that now that I have everything dependent on time, I'll need to include that time dependence. Okay, so let's do it. Cos phi t r hat. I'm going to make sure to include that r hat is itself dependent on t here, actually. Minus sine phi of t phi hat. And just to be clear, the reason that r hat is dependent on t is because it depends on x and y of t. So it's implicitly dependent on t through those other variables. Good. Okay. So we get that. Now we need to copy down the y double dot times y hat. So now I'll say plus oops, that should be cosine. All right, and now for y, sine phi r plus cos phi hat. Oops, of t. Great. Okay, now we need to go through the somewhat laborious process of figuring out where we have cancellations. Okay, so let's go term by term. First, we have a term that depends on r double dot up here. We have a similar term that depends on r double dot down here. And once again, I screwed up. This should have been a sign. Need to avoid that kind of error if I want everything to cancel as it should. All right, so let's see. We have an r double dot times cosine phi times cosine phi times r hat. R double dot times sine phi times r hat. Those two will combine together to give me an r double dot of t times r hat of t. Again, through the Pythagorean identity, cos squared plus sine squared is 1. Good. Now, on the next, on the phi hat part, I'll get r double dot cosine times minus sine for this first part, and then r double dot sine times plus cosine. So those actually cancel, so I don't need to worry about them. Next, I have this term here. So let's see, this is minus r dot phi dot sine phi times cos phi times r hat plus 2 r dot phi dot cosine times sine. So the sine times cosine appears in both, but once with a minus sign. So the r hat term cancels. All right. Then the phi hat term, let's see. We get plus sine squared here, plus cosine squared here. So we'll get plus 2 r dot of t phi dot of t times phi hat of t. Good. And notice the sines and cosines have actually canceled out in both cases. All right. Next up, we're at this term, where once again, I think it looks like if we are careful, we can find everything that cancels. So here we'll get minus cosine squared minus sine squared. So that looks like it's going to give us minus r of t phi dot of t squared times r hat of t. Whereas this second term is going to cancel. We'll get cosine plus cosine phi sine phi, and then a minus cosine phi sine phi here. Good. All right, next up, this last term here. So this is our phi double dot term. Looks like our cosine r of t is going to combine with it in this first case, and down here we have a cosine times sine, but attached to no minus sign, so there's going to be a cancellation. And then for the second term, we will get things to combine. So this is going to give us a plus sine squared up here, plus cosine squared down here. So plus r of t times phi double dot of t times phi hat of t. And I can combine these, right? So I'll get r double dot of t minus r of t phi dot of t squared times r hat of t plus 2r hat of t, r dot t phi dot t plus r of t phi double dot of t phi hat of t. Great. Okay, and this all, again, was to give me the left-hand side of Newton's law, Newton's second law, I should say. So now, whenever I see Newton's second law, if I had F given to me in terms of r and phi, suppose, for instance, I had a force that always pointed away from or toward the origin, then I could write it down in polar coordinates and find something like this quite easily. All right, now, I hate to sort of have led with the more gross, terrible way of doing this. But in fact, there is an easier way in this case. So in this case, and by in this case, I mean the case of polar coordinates, there is an easier way. Now, in this course, we're going to deal with cylindrical coordinates, polar coordinates, and spherical coordinates, principally. And actually, this technique will work in all of those cases. I mentioned it back on the light board, and it's kind of important to say here. What we can do is also put the position vector, or consider the position vector as a vector of the correct length living at the point in question. So to go back to my drawing, if this is our trajectory, don't really need that, and this is the velocity vector, the acceleration vector would be what, something like, I guess if this is the inscribing circle, something like this. And the position vector now is the same as the length from the origin to the point, but actually I'm going to put it at the point, so this will be the position vector. Now I can do something quite clever. So let's think about the position vector as being r. And because this is a trajectory, r now depends on t. All right, but now, crucially, r, this vector, is proportional to the r hat unit vector. It's in the same direction, except it has length r, the distance from the origin to the point in question. So r, to give an equation that sounds a little funny when you say it out loud, r vector is equal to r scalar of t times r hat, again, of t. Great. Now I can take a derivative of this, a time derivative. Now you might wonder, how do I take time derivatives of this kind of scalar vector product? And the answer is just by the product rule, exactly as you would think. So this is going to give me r dot of t times r hat of t plus r of t, r hat dot of t. Now what is r hat dot of t? That's an interesting question. And how would I answer it? Well, the answer is that I would go back to my definition of r in terms of these things. So let's do it. R hat is equal to cos phi x hat plus sine phi y hat, right? Now, if I take a time derivative, if all of these things depend on time, I won't write in the time explicitly on this line. Now I'll get that r dot of t is equal to, okay, well, I need to take a chain rule of this cosine. So I'll get minus sine phi of t times phi dot of t x hat, because x hat does not depend on time, and then plus cos phi of t, phi dot of t, times y hat, which means I can actually just pull that phi dot, out, and now I got minus sine phi of t, x hat. Let's make sure that this calculation is not confused. Plus cos phi of t, y hat. Excellent. Okay, now I'm going to scroll right back up here, and I'm going to look at what my phi hat vector is. It's minus sine phi plus cos phi. Sorry, minus sine phi x hat plus cos phi y hat. Scroll back down here, I notice, oh man, that's exactly what I have here. So this is exactly phi dot of t times phi hat of t. Just for comparison. Wonderful. Okay, so now I can rewrite this equation. R dot of t, r hat of t, plus r of t, phi dot of t, phi hat of t. Great. So that is the velocity vector, r dot of t. Now what about the acceleration vector? Well, I'm just going to play the same game again. R double dot of t will equal, okay, so for the first term, I'll use the product rule. R double dot of t, r hat of t, plus r dot of t, r hat dot of t. Okay, now for the second term, I'll need to use the product rule 3 times, right? So, or on the 3 factors, I should say. R dot of t, phi dot of t, phi hat of t, plus r of t, phi double dot of t, phi hat of t, plus r of t, phi dot of t, phi hat dot of t. Okay, interesting. So let's see. The one thing that we can do right away is just stick in that this is phi dot of t, phi hat of t, which we found in the last step. That means that this term, r dot of t, phi dot of t, phi hat, can actually combine with this term. The last thing that we need to do is figure out what this is, phi dot of t. So let's go ahead and do that. Sorry, phi hat dot of t. And we'll just do that the exact same way. So this was, recall that phi hat is equal to minus sine phi x hat plus cos phi y hat. Okay, so now phi dot is going to be minus cosine of phi of t, phi dot of t, x hat, minus sine of phi of t, phi dot of t, y hat. And after just a little bit of rearranging, you'll see that this is minus phi dot of t times r hat. The minus comes because this r has 2 plus signs, plus cos phi x hat plus sine phi y hat, but we have 2 minus signs down here. Okay, so now when all is said and done, we can write in the final answer, which is r double dot of t, r hat of t, plus 2 r dot of t, phi dot of t, phi hat of t, plus r of t, phi double dot of t, phi hat of t, and then minus, because of this minus sign here, r of t, phi dot of t squared, r hat. Oops, this should have been of t, r hat of t. If I group things in the way that I did before, we will see that these two equations are exactly alike. Plus 2r dot of t, phi dot of t, plus r of t, r phi double dot of t, all of that times phi hat of t. And yes, this is exactly the same as what we had here. Okay, so in this case, we have an easier way. All right, now we've done all of this hard work. Let's actually do a couple of examples. All right, I think the easiest one to start with is the just something that's undergoing motion in a circle, uniform motion in a circle. We know that something undergoing uniform motion in a circle must have force being exerted centripetally, so toward the center of the circle at all points. And we need to have, let's say that's F centripetal, that the magnitude of this force is mv squared over r. So let's say that our circle has radius capital R. Great. Okay, so now let's go ahead and actually just figure out Newton's second law in this case. So what I would have, just, from what I just wrote, is minus mv squared over r times r hat, because this force is in the r hat direction, or the minus r hat direction, is equal to, okay, so this is the force side. On the, I should divide by mass like I did up here. So actually, let me get rid of that m. Let me also replace v. Well, I'll replace it. I'll replace it in a second, actually, because we need to think about what v should be. All right, and that is equal to, well, this thing that I've written a bunch of times over here. So r double dot of t minus r of t phi dot of t squared r hat of t. Well, actually, I'll drop the dependence on t, but it's still there. It's just implicit. 2 r dot of t phi dot of t plus r of t phi double dot of t phi hat. Okay, now what is this v? V is the linear speed that the particle has right now. But I can relate that linear speed to an angular speed, which is often called omega in this context, as v is equal to omega times r. Okay. And so actually, sometimes this is written omega squared times r, rather than v squared over r. Omega, it turns out, is equal to the angle covered per second. But that's exactly what phi dot is. So that's the number of radians covered in a single, unit of time. So actually, this whole left-hand side could be phi dot of t squared times capital R. Okay, now this is a vector equation, so it breaks into two components. It breaks into its r component, and it breaks into its phi component. But notice the left-hand side has no phi component, so we can actually break this into, let me make sure that this is clearly an example. So we can break this into two parts. The first one, in the r hat direction, is going to be minus phi dot of t squared r is equal to r double dot of t minus r of t phi dot of t squared. Okay. The second one is going to be equal to, 2r dot of t phi dot of t plus r of t phi double dot of t is equal to 0. All right. Now, solving these equations is actually kind of non-trivial. This is a case where we know what the right answer is. We know that we should have uniform motion in a circle. That means that we should have that r of t is a constant, and phi of t is just linearly increasing around the circle. Okay, but these differential equations are a little bit hard to solve. We actually have to work kind of hard to figure out that that's right in this case. How are we going to do it? Well, we need to move things around just a little bit. I want to move, let's say, this to the other side. So I'm actually going to start with 2. I'll have r of t phi double dot of t is equal to minus 2 r dot of t times phi dot of t. All right. Now, I am going to do something that maybe people haven't seen before. I'm going to take this phi dot and divide it to the other side, and this r and divide it to the other side. So I'll have phi double dot of t over phi dot of t is equal to minus 2 r dot of t over r of t. Okay, and this may be a strategy that you haven't seen before when solving differential equations, and if not, know that it is a very common one. Anytime you have the derivative of a quantity in the numerator of a fraction, and then the quantity itself in the denominator, that's the same thing as the derivative of the log of the quantity. And you can go ahead and check that using the chain rule yourself. So this is exactly equivalent to saying that the time derivative of the log of phi dot of t is equal to minus 2 times the time derivative of the log of r of t. Okay, well now I can simply go ahead and integrate both sides with respect to time. Then I use the fundamental theorem of calculus to tell me that because these two things have the same derivative everywhere, they're the same up to a constant. So this implies that the log of phi dot of t is equal to minus 2 times the log of r of t plus a constant c. Okay. Now, I'll need an initial condition in order to solve this system of differential equations, and I might as well use that initial condition now. Let's say that at time t equals 0, so at t equals 0, I'm going to have r of t is equal to capital r dot of t is equal to 0, phi of t is equal to 0, and phi dot of t is equal to omega. And we'll see what happens. Now, if I stick in my initial condition here, so I'll say initial condition, this will tell me that the log of omega is equal to minus 2 times the log of capital R plus C. Ah, okay. Terrible, terrible, right? I can't take the log of a dimension-full quantity. What I'll need to do is, if I still have any dimension-full logs at the end, I'll need to use this constant to cancel them out. But as we'll see, this actually will end up being okay. Okay, so what am I going to do? I'm going to move this minus 2 inside the log using log rules. Then I'm going to move the whole thing over to the other side with a minus sign. So log of omega, maybe I'll do this in a slightly different order actually. Log of omega plus log of r squared is equal to c. That implies that c is equal to the log of omega r squared. Okay, and it turns out that by expressing c in this way, we fix all of those dimension issues that I was just mentioning. So we have the log of phi dot of t is equal to minus, well, actually, let's say it like this, is equal to the log of omega capital R squared over little r of t squared. Good. This still doesn't quite have the right dimensions. I still need to cancel out this angular velocity, but it actually is an issue on either side, which ends up canceling out. Logs can just be funny with dimensions like that. Watch out for that kind of thing. All right, so now, have I actually solved the differential equation? No, because I have this, but I don't have the solution for phi itself. So the way to solve that would be to take the exponential of both sides. Taking the exponential of both sides is just going to get rid of the logs. Okay, so this is going to tell me that phi dot of t is equal to omega r squared over little r of t squared. Okay. Now, I can't integrate this because I don't know what little r of t is. I don't have a solution yet for that. So that now I need to come up to my number 1 equation. And what I'm going to do is go ahead and just stick that in. So actually, if I move this around a little bit, I can get that r double dot of t is equal to r of t minus capital R times phi dot of t squared. Good. And I just solved for phi dot of t. So this is going to tell me that phi dot of, that r double dot of t is equal to r of t minus capital R times omega squared r to the fourth over little r of t to the fourth as well. Okay, now at this stage, it doesn't look like we've done something sort of incredible, but we have. We've gotten down to just one second order ODE in the variable r, or in the function r as a function of t. And the nice thing about second order ODEs, as long as they're sufficiently nice, which this one is that they at least have solutions, and those solutions are unique once we specify initial conditions. Now in this case, we have specified the initial conditions here. This equation itself would be really hard to solve, but we already have a really good guess for what the solution is. It's just r constant. And our existence and uniqueness conditions say that if we happen to guess the solution, then we did it, if it meets the initial conditions. So let's check that our initial conditions, that our constant solution rather satisfies both the initial conditions and satisfies this equation. Well, it certainly satisfies the initial conditions because it was concocted to satisfy the initial conditions. So again, our trial solution is r of t is equal to capital of R. Okay? Now, if we stick our trial solution into the differential equation that we came up with, we would get that 0, because the second derivative of a constant is definitely 0, is equal to r minus r, which is 0, times omega squared r to the fourth over capital R to the fourth. And in fact, 0 is equal to 0. So we did it. This feels a little bit perhaps anticlimactic because we did it by guesswork, but it does show that everything that we were doing here works out as expected. All right, let's do an example that is a little bit less trivial, and then we'll call it for this video. Let's do a good sort of physics 101 type problem where we have a pendulum swinging on a string. So here's a pendulum, length L, mass M. Here we'll call this angle, so we'll put our x-axis in this direction, kind of strangely, so that this angle is phi. All right, wonderful. Now let's do a classic free body diagram for this problem. We have the force of gravity, mg. We have the force of tension that goes in this direction. And those are going to combine to define the motion of this thing. Now tension is going to make sure that this doesn't move in the r direction. So the tension will be concocted to do that. All right, before we get too far ahead of ourselves, let's rewrite everything into the r and phi directions. All right, so at this point, mg is going to be in the minus phi hat direction because phi hat is this way. And this angle being phi turns out to make this angle also phi. So it looks like our phi hat component of gravity is going to be mg sine phi. All right, so let's write our equations now. In the r direction, we're going to have mg cos phi minus the force of tension. And then in our phi direction, we're going to have minus mg sine phi phi hat. Good. Everything here depends on t. I'm just not writing it in for the time being. Then we're going to have minus, well, we got to copy our stuff from up here. Oops. Probably should pull that down to about here. Good. Okay, these two equations give us everything we need. Now, the force of tension is going to mean that we actually have zero motion in the r direction. So this is going to all give us zero because the tension is actually just a force of constraint. Okay, so now we get r double dot of t minus r of t phi dot of t squared is equal to 0. That's our first equation. And our second equation is 2r dot of t phi dot of t plus r of t phi double dot of t is equal to minus mg sine phi. And let's jump ahead to the part where we know that r dot is equal to 0 and that r is equal to L, because again, we included a force of constraint. So this is going to equal 0, and this is going to equal L. So this gives us L phi double dot of t is equal to minus mg sine phi. But look, this is just an equation in phi. It's a second order, almost linear equation. And why do I say almost linear? Well, the answer is that sine phi for small angles obeys the small angle approximation. So this is approximately equal to phi if phi is small. And without even working very hard, we have, and where did I screw this up? I forgot to divide by m. That was my fault. So this is all true if I throw an m around this entire side of the equation. All right. In any case, so now if I get rid of that m, this gives me the exact form of the pendulum oscillation equation that people are familiar with. Root g over L, or sorry, times g over L phi is approximately equal to 0 for small angles. So there's a slightly more useful example of where this works out really, really nicely. If we decide to work using these polar coordinate vector or polar basis vectors and polar coordinates, we actually simplify the calculation quite a bit. All right, so this is just a little primer on this stuff. Obviously, it's going to take a lot of practice before you get used to it. Fortunately, there will be a lot of time during the course to continue practicing using polar coordinates and the polar unit vectors. So I will see you in the next part of this lecture on non-dimensionalization, and thanks so much for watching.